This is the continued commentary for the acetals, ketals, and carbohydrates slides. So going to slide showing the stereoisomers revisited. So this slide is actually taken from the first chapter 1-2 handouts, and there were two types of isomers that we were going to focus on. The first one was enantiomers, the second one was geometric isomers. If you recall, I skipped the enantiomers portion and focused on the geometric isomers. Now I'm going to do the opposite. I'm going to skip the geometric isomers and focus on the enantiomers. Isomers are structures where they have the same molecular formula, but they have the same connections, but they have different spatial arrangements. So highlighting this portion right here, different permanent spatial arrangements. So briefly going back to our second category called geometric isomers. If you recall, whenever we had a alkene or a cycloalkane, we would have branches or functional groups either on the same side or opposite sides. So they had the same connections, same molecular formula, but different spatial arrangements, and these were permanent. Now we're going to explore something similar called enantiomers. So these are structures where they have the same molecular formula. However, they have a different spatial arrangement. So same molecular formula, let me say it again, same connections, but they have a different spatial arrangement. In order to have an enantiomer, you need to have a carbon, and we call this a chiral carbon. I'll explain the name a little bit better in another slide, but here I've went ahead and I circled and I showed an arrow to the black portion of this model right here. That's a chiral carbon. Notice how it has 4 different groups surrounding it. So, here we have a molecule with a chiral carbon, and we say that this is an enantiomer because if we were to sit there and place it near a mirror, its reflection would be this molecule to the right. So, these are termed mirror image stereoisomers. Mirror image stereoisomers. That's the term for them. Another way of figuring out if these are stereoisomers is if you were to sit there and move this over, would each of the groups take up the exact same space? If they would, then they are superimposable. If they don't, then they're non-superimposable. And if they're non-superimposable and they create perfect mirror image forms, then they're stereoisomers called enantiomers. So a lot of terminology here. Let me go ahead and summarize this again, and I'm just going to go ahead and use my hands as a beginning example. So going to the white screen. Here is a outline of my left hand. If I were to sit there and place my left hand near a mirror, so that rectangle thing is a mirror, then its reflection, if I have enough room, would create a mirror image form of my right hand. So, notice these are mirror images to each other. So you can think of my left and right hands as enantiomers. Now, I could not place my right hand into my left hand and have each of the digits match up. So these are non-superimposable. So defining enantiomers one last time. Enantiomers are non-superimposable mirror image molecules. Let's go to actual examples now. Let me go ahead and create a new white screen. So this is an attempt to draw a three-dimensional molecule. And we need to do this in order to accurately represent these potential enantiomers. Let's see. I'll use iodine. So, here is what's called a wedge-dash sketch. A wedge-dash sketch. W-E-D-G-E dash dash. The wedge is this right here, and it shows a blackened triangle coming out, extending out from the carbon. So the wedges means the group is coming out. The dash means the group is going into the screen or into the plane of paper. And the traditional lines means these are on the same plane as the screen or your piece of paper. Now, I'm going to do the same thing. I'm going to draw a makeshift mirror, and I'm going to draw its mirror image. Its mirror image would look like this using the wedge-dash structure. So this is the mirror image. So we would say that these are enantiomers. These are enantiomers. Okay. Now, in this instance right here, we talked about wedge-dash sketches, and we talked about enantiomers. We also talked about the fact that if we have two enantiomers, these are non-superimposable. Oops. So non-superimposable. That screen came in the way, so you'll have to finish that on your own. Non-superimposable. So I cannot place the right into the left and have the groups perfectly match up. They would be different. In order to have them match up, I would have to move the orientation of these groups around. And normally these are fixed. So if we move the orientation around, then they might be superimposable. If they are superimposable, then it's the same molecule. So let's go ahead and take a look at this example right here. So again, these are enantiomers. Now, It turns out that in the biochemistry world, nature prefers only one type of enantiomer. So it could either like the one on the left or the one on the right. Consequently, we need to label the enantiomers. Organic chemists, they label them R and S for the left-handed or right-handed isomer. In biochemistry, they label them as D or L. D for dextro, L for levo. And we'll investigate those naming schemes of enantiomers in the next slide. But for right now, here are two very popular R and S using the organic enantiomer naming scheme. So it turns out that enantiomers are very important. And for example, just as the body prefers one over the other, it turns out drugs can have different effects depending on whether you have a R or S enantiomer or opposite enantiomers. So in this example right here, the R enantiomer, when it goes into the body, it actually puts the person to sleep. So this was actually prescribed in the 50s to pregnant ladies in order to have them have a good night's sleep. Unfortunately, the S enantiomer has different effects on the body. It turns out the S enantiomer will actually inhibit the growth of new blood vessels. You might find the new growth of blood vessels in growing fetuses, for example. So it turns out pregnant ladies, given this particular drug that had S-thalidomide present, gave birth to babies with missing arms and legs because their arms and legs couldn't develop the blood vessels in order to sustain their growth. So consequently, these were referred to as thalidomide babies. So it's very important in both organic and biochemistry to not only know of their existence of enantiomers, but also to know which one you have, which orientation you have. So here we have a biomolecule, L-glyceraldehyde, and here we have another one, its mirror image, D-glyceraldehyde. L and D refer to the two types of the mirror image stereoisomers. And it turns out that the D isomers are the types of sugars that the body likes to use. It prefers D over the L. If you put L in the body wouldn't know what to do with it. It would either treat it as garbage or it might have some unwanted side reaction. D, however, is the one that it actually uses. So it's pretty amazing. You can have all different types of isomers for a particular biomolecule, but the body only likes to use one, and it will create, maintain, have byproducts of only one type. So going back to the wedge-dash structure, this right here is a wedge-dash. Notice the wedges are coming out on the horizontal line and the dashes are going in. This is the common way that I'm going to test you on wedge-dash structures. I will try to keep the horizontal as wedges, the vertical as dashes. So, why would I do that? Well, it turns out, and jumping ahead a bit before we investigate D and L, so if we go forward 2 slides, it turns out biochemists, like organic chemists, can be lazy at times. So this is their sketching notation when they want to be lazy. On the horizontal lines, it's implied to be wedges. On the vertical lines, highlighted with my yellow pen, these are implied to be dashes. So using the Fischer projection, we can immediately let other biochemists know which ones are the wedges and which ones are the dashes, provided we keep it in this format right here. I also want to point out to you, using Fischer projection, that this works exclusively And all my examples, as far as the upcoming tests and so forth, will stick to this rule. It works exclusively with sugar molecules. Sugar molecules will have a carbonyl group at some point. If it has a carbonyl group at the end, then it's the aldehyde, in which case we represent it as CHO. And CHO means aldehyde. Also notice we always show the hydrogens. So unlike traditional organic line angle, biochemistry Fischer projections always show the hydrogens. And finally, at the bottom, we tend to end with a condensed form, showing the last carbon along with its hydrogens in condensed form and along with the alcohol in its condensed form. And the majority of the carbohydrate monosaccharides, they always end in this part right here with a CH2OH. You will be expected to sketch from Fischer projection to wedge-dash structure to Fischer projection. You'll be expected to sketch between these, vice versa. So here is a better artist's three-dimensional rendering of a structure, of a particular L enantiomer. Here is its Fischer projection. I'm sorry, here is its wedge-dash structure. Let me label that as wedge-dash. And then going down using the highlighter, this is the Fischer projection. So I screwed up when I labeled those two. Let me say that one last time. Here is the artist's rendering. Here is the wedge-dash. And then here is the Fischer projection. You're responsible for sketching the wedge-dash and Fischer and vice versa. So let's go ahead and go back to our assignment. So in this case right here, focusing on this molecule right here, automatically I can tell that this is not an enantiomer. It's not a candidate for being an enantiomer to begin with. Why? Because it does not have 4 different groups. Because it doesn't have 4 different groups, we actually call this a chiral, with a meaning not. Let's go to this one over here. This one is a candidate for being an enantiomer. Obviously, we could make a mirror image of it, but more importantly, it contains at least one carbon with 4 different groups attached. In this case, and I'll go ahead and I'll highlight this in red, this is called the chiral carbon because it has 4 different groups attached. So this has a chiral carbon. It's possible to have many chiral carbons in the same molecule, and that particular molecule will have many different stereoisomers. Although we will only focus on one of its mirror images. It could have other forms, and those would be non-mirror images, what we call diastereomers or mesocompounds. Basically, it's other terminology you're not responsible for knowing. You'll just be responsible for identifying, can a molecule be an enantiomer? If it can be an enantiomer, what is the criteria for it? The criteria is very simple. 1, can you create a mirror image of it? And 2, does it contain a chiral carbon? So, wrapping this up, you can go ahead and create a mirror image. Here is its mirror image. All I'm going to do is change the side groups and voila. Here we have its mirror images. And so this right here is an enantiomer of this one because it has a mirror image and it has a chiral carbon. So in this case right here in B, it would be no. However, in C, it would be yes. I also want to point out, and I'm not going to emphasize this anymore, but whenever you have mirror image isomers, those are non-superimposable. Their groups cannot occupy the same space and line up properly. So, as far as drawing the Fischer projection, very simple. Automatically we assume that the wedges, horizontal wedges, those would be lines. The vertical dashes would look like this. And voila, here is the Fischer projection. So not a lot of changes needed in this instance. Let's go ahead and do this top left one. We'll go from Fischer projection, and I'll draw the same molecule, only I'm going to turn it into a wedge-dash structure. So the horizontal are always going to be wedges. And the vertical will always be dashes. Voila. And this concludes this portion.